But it's 7 o'clock. So I want to hand it over to Mike, AD4MM. He's got a good thing about NanoVNA, right, Mike?
Actually, it's three of us.
Oh, well,
So, Dean is going to kick it off, huh?
All righty. I'll hand it over to Dean in that case. Dean, if you want
to.
Thank you.
Go for it.
Sounds fantastic and fine business. Okay, so we're going to talk about the NanoVNA. This is my NanoV in action as part of our maker group build. Some of our makers will recognize my low-pass filter, which never worked as well as this trace made it seem like it ought to work. But that has nothing to do with the NanoVNA. It has to do with the cheap Chinese capacitors that are on the board. So this is the NanoVNA. We're going to talk for the next few minutes about kind of what this thing is, what it's good for, what you should use it for. This is a test. This is just a picture off of my bench. I was testing this low-pass filter, and it shows you kind of what the performance of the filter is. Next couple of minutes, I want to talk about why a NanoVNA. Well, first off, it's very inexpensive. It's around $60, and it makes this technology, vector network analyzer, available to ham radio operators and hobbyists. And this is only in the last couple of years. Devices that do what this does have been very, very expensive before. So here's what we're going to cover in the next few minutes. What's a vector network analyzer? What's it good for? What can you measure with it? Then I'm going to turn it over to KD4MM and KA4CDN, and they're going to kind of show you kind of some examples of how you could use it. So first order business, vector network analyzer. It, plain and simple, is a test instrument that measures and characterizes RF devices, filters and amplifiers, and anything that passes RF in and out. You can measure with, or just in and reflected, you can measure with a VNA. It measures the magnitude and the phase of reflection and transmission properties of the ports of a device versus frequency. And now, as I said, these used to be only used by RF engineers because they were very expensive, $5,000, $10,000. Some of them were as much as $250,000. And if you're in the kind of, cell phone industry, or you're doing, you're looking at very, very extremely high frequency capabilities, that's the kind of device you need. But for hams, for amateur radio operators, due to the rapidly lowering price of, silicone and some very clever engineers, we now have a device that's available for around $65. And you can get it from rndl.com for $65, and it's a terrific device. I'll talk a little bit more about where to get it from later. So let's talk a little bit about terminology. VNAs, because they weren't designed by amateur radio operators, use strange sounding terminology like DUT. Well, what's a DUT? It's just the device under test. It's the thing you're testing. Could be an antenna, could be an amplifier, could be a filter. Anything that takes a source signal in and produces something out can be a device under test. So the device itself affects the signal that is sent through it. It affects the signal going through it, and input impedance affects the applied signal and shows back as reflected power, like if you were testing your antenna with an antenna analyzer. And the important thing here is it allows you to understand the complex impedance of the device you're testing, which is really important. If you remember from your tests, Smith charts and complex impedance, and it allows you to visualize that. It actually displays a Smith chart and makes it very easy to see these sorts of things. And this is really important if you're designing matching networks, whether for an antenna or, as our maker group is doing, components inside a radio. It's a really, really useful device for doing that sort of thing. So big concept, device under test, source in, signal out, source signal in, signal out, and it does some things. Okay, so this is a basic visual for what a VNA does. It you send a source signal in. The reflected power is the flower that you see is the signal that you see coming back. The reflected signal is the signal that you would see coming back from the input, and the transmitted power, the transmitted signal is the signal that goes through the device. And a VNA measures the magnitude and phase of those two signals. That's all it really does. It measures the magnitude and phase, and then there's a bunch of different ways to display it that are useful depending on the kind of things that you're doing. So it knows basically what the magnitude and phase of the source signal is because it generates the source signal, and then it compares the source signal to what it sees reflected and what the transmission is. So signal to and through the device under test. Okay, now that's a NanoVNA. Couple of things to note here. When you're talking about VNA measurements, you'll hear terms like the S11 measurement or the S21 measurement. And those are called S parameters. S stands for scatter. I don't even actually know what it means. One of our engineers can tell me what that scatter means. But the bottom line is the way you understand what an S parameter is, it's the ratio of a measured response to a stimulus. So SXY, S11, is the response at port X resulting from a stimulus applied at port Y. So S11 is a response at this port from a stimulus at this port. Now, the NanoVNA calls them channel 0 and channel 1. Ignore that because everybody else calls them S1 and S2. So channel 0 is S1, channel 1 is S2. Sorry, they labeled it that way. If you've got a little bit of tape, you can tape over it, call it S1 and S2. That's what they are, and all the descriptions you're going to see are going to call them S1 and S2. So S11, the response at port 1 from a stimulus at port 1. So you send a stimulus out, you get a response back. That's a reflected measurement. S21 is the response at port 2 from a stimulus at port 1. So that's a transmission measurement. So reflection measurements measure things like visibler, return loss, input impedance. Transmission measurements measure things like the gain and loss of an amplifier or a filter, the transmission coefficient itself, S21, the phase delay of a transmission. How much is their delay that, of the phase that, as it goes through the device? So those are kind of the key things to know about a VNA. Again, it measures the transmitted and reflected signal going through a device. S11 is the reflection measurement. S21 is the transmission measurement. Now, more expensive VNAs, you can also do an S12, and you can do it different directions. These little inexpensive ones are really one way. You transmit out, you generate a signal out of port 1, and you either measure it as reflected back to port 1 or transmitted through the device to port 2. And so that's kind of it for what a NanoVNA does. Well, what can you do with it? Well, a single port measurement, so you don't even need the second port. You can measure SWR just like you would with an antenna analyzer. You can measure complex impedance. You can measure components like resistors and capacitors and inductors. You can measure the feed line length of a feed line. You can measure the distance to a fault in your feed line. What could you do with a transmission measurement? Well, filter shape and loss, like the one I showed at the beginning. How's your low pass filter working? How does your band pass filter work? How does your band stop filter work? Loss in a feed line. How much loss are you getting by through your transmission? Delay in a device under test. Gain and frequency response of an amplifier. I got distance to a fault. That's a typo. That's twice on there. It's only on the left, not on the right. So what can you measure? Antennas, duplexers, diplexers, filters, inductors, all the things that are of interest to us as amateur radio operators can be measured. Many of the things can be measured with a vector network analyzer. This is a really, really useful device. In fact, if you're not a maker where you're actually building circuits, this is probably one of the most useful tools to have in your toolkit as an amateur radio operator. You can characterize your antennas, you can characterize filters. There's all kinds of things you can do with this device, and it's really, really inexpensive. Even if you just use it as an antenna analyzer, it's less expensive than the big bulky boxes from MFJ that take 9 batteries and last for about an hour before you get to change the batteries. Like I said, it's more useful than an oscilloscope for many applications that we use. There's a bit of a learning curve, like the nomenclature, but there's great resources all over the internet. If you haven't discovered Alan Wolke yet, and you're any kind of technical nerd like me, you're going to love these videos. So he's got a full suite of videos just on the NanoVNA. And he's got hundreds of other videos too, but you can learn everything you want to know about using this device by looking at his videos. You know, measure a low pass filter. Well, that's what I was doing at the beginning. Measure an antenna system. He tells you how to calibrate it. That's one of the deals with these things, is they have to be calibrated. We're not going to go into all that tonight because we don't have enough time. But just to give you an idea, there's a huge amount of material available. NanoVNA.com is the website that talks about them. One thing I want to point out is if you're going to buy one, use their link, buy a NanoVNA, and buy from one of their preferred buyers, because there's a bunch of clone makers, and some of them are no good. Some of them are duds. So, but if you buy from one of these, and I buy mine from RNL Electronics, you'll get a reliable one, and they'll be great. So there it is at RNL Electronics, $64.95, 4-inch screen, 10 kilohertz to 1.5 gigahertz. Really cool device. So that's it for the kind of the rapid fire intro to NanoVNA. Let me turn it over to KD4MM.
Thank you, Dean. Okay, I'm going to go through rather quickly some of the uses of the NanoVNA for antenna system analysis. And tonight we're really on a sort of a fast cruise to show you some examples of what it does, and probably not going to satisfy a lot of people's questions and things. So if you're interested, we can come back later, maybe with some experts next time. So let me get started here. So I'll cover a lot of what Dean just covered about measurements for an antenna system. You can measure VisWAR, which is very, very useful. And so if you're thinking about saving up for that $300 antenna analyzer, you might want to take a second look at this for $65, because it'll do a lot of the same things and more. Measures impedance, absolute complex impedance as well. You can take a look at your cable length, and you can identify discontinuities in your cable, which might be faults, or it could just be an impedance change. Maybe you've got 2 types of cable, and you can actually see on this thing the change from a 50 ohm cable to a 75 ohm cable, for example, right on the screen. And you can also measure the quality of your cable, the insertion loss, and compare it to what the advertised insertion loss is. Okay. As Dean said, you'll see the Nano out there in different screen choices, 2.8 or 4-inch screen, and you've got a full set of capabilities on a very small screen. But if you really, really have trouble with that, you can use a laptop, plug the Nano into it, and there is free software available that will allow you to see what you see on the Nano, plus have some additional capabilities. And I'll just quickly show you the difference here. So here's my Nano. I've got the 4-inch screen, and which is pretty good. But then if you go to a computer, you get a whole set of screens, and on the right you can see 4 data display charts, and you can display up to anywhere from 2 to 6. So you've got a lot more capability, and there's a lot of other things on the screen that I won't get into detail on. A lot more data at your fingertips easily. Okay. Other thing, if you're going to get serious with this and do it to take a look at your antennas and other systems, you'll probably want to invest in a couple simple accessories. Male SMA to PL259 adapters are essential for working with antennas, and a male SMA to pigtail with alligator clips, because sometimes maybe you're working on cable antennas that don't have connectors, and then finally maybe some reading glasses if you're going to stick with a 4-inch screen. So I found helpful once in a while. All right, I'm going to go through a couple examples of how I've used my VNA on the antenna team in particular. Mike Imany and I went out to help Kurt, K9 VA, with an antenna repair. He was having some trouble with his 80-meter end-fed antenna, half-wave antenna, and they were suspected some feed line issues, and we just sort of wanted to generally upgrade things. So I stuck the VNA on his antenna, and this is actually after we had addressed some feed line issues, and this is kind of what you get out of it. And again, I won't go into a lot of detail, but you can see for his antenna in that chart in the middle there, sweeping from 3 megahertz to 30 megahertz, he's got a lot of nice low VISWAR points, resonant points for an antenna. The VNA, I'll go to the next one. You can also zoom in. This one, we took a sweep at 40 meters. We swept each of the bands. And the VNA has the ham bands indicated on there by that gray zone. And you can actually change the size of the bands if you want to put something else on there. This software has a tremendous amount of variability and adjustment in terms of displays and things. So right now I'm showing the Smith chart, VISWAR, complex impedance, and the absolute impedance. But you can actually, there's a whole selection of S11 and S21 parameters that you can show on any of the 2 to 6 charts that you want to put up there. And you can see on the left in the middle, you've got marker 1, marker 2, marker 3. There are 3 little markers you can click on, put anywhere on your screen, and they'll give you at that particular point on your curve the data you see on the left there. Okay, so frequency, impedance, VISWAR, return loss, quality factor, phase, etc. Okay. The other thing is at the very bottom of the screen, you'll notice there's an analysis button for a lot of the things that the VNA looks at. You can do VISWAR analysis, bandpass filter analysis, low-pass filter analysis, and it'll actually take a look at the data that you provided, and it'll give you the information. For this case, for VISWAR, you can set the VISWAR limit that you're interested in, and it will look at your chart, and it will tell you what the start, minimum, and end, and the span of your VISWAR is, for example, over that frequency range, which can be a nice quick glance thing. Okay. All right. So that's Kurt's antenna, which that all went very well, and we actually did upgrade the feed line. Found out there were some issues with one of the connectors actually. The next one was I went over to John Acton's house a couple weeks ago, again, Mike and I, and he was concerned that in some work up in their attic with adding some insulation that his antenna feed line had been disturbed, and he wasn't sure if it was still good or not. So rather than pull the whole thing out, which would have been quite a job, we stuck the VNA on it, and we used a feature of the VNA, which is time domain reflectometry. And TDR, which is a really cool capability, is simply, if you want to look at it as a sort of a gross generalization, it's kind of like a sonar or a radar, and you're sending a pulse out down the cable, and you get a reflection back if there's any discontinuity. If you've got a conductor that's uniform impedance and it's properly terminated, there won't be any reflections at all. So what we were looking for was a clean cable with no reflections, no variations, and that's what we found. So that was very good for John. And the other thing we did, let's see. So that's that. And there's a chart. If you get, again, I'm using NanoVNA here, the software, to show you, but you can pull up a TDR screen and you can actually select your cable type. In this case, RG8U Belden 9913. It gives you the velocity factor, which you need to, because you're calculating the speed of the wave down the line and the reflection back. So, and this is one that I did on, because I didn't capture what I did over at John's house. Unfortunately, that would have been a nice display, but I measured my feed line tonight, and it says I've got an estimated cable length of 103 feet, and that's within about a foot what I have out in my backyard. So this thing works quite well for measuring feed line length. You can also measure feed line length using the Nano. It's got a transform function built into it, and which shows you the reaction to an impulse, a low band impulse. And again, this shows 32.3 meters. If you look in the upper right screen, you can very clearly see where I've got a discontinuity in my on the Nano screen, sending a pulse down the line. And this is just an S11, just a single port measurement. So it's, again, really handy thing to have in your pocket. The other thing you can do is you can measure feed line insertion loss measurement. What's the attenuation your cable and your connectors as a combination give you? So again, I stuck my, I actually had 110 feet of 9913 laying around with connectors. I plugged it into the VNA, and you get a nice, from 3 megahertz to 30 megahertz, look at the insertion loss for your cable. And this is probably within, when I looked at the Belden 9913 parameters, my insertion loss, as you can see it on the chart there, is about within about 5% of what it should be. So I was very happy with that. Okay. All right, and then last, you can stick a rubber ducky on this thing and you can get a pretty nice analysis of that too. I decided to do that with my little Anytone rubber ducky, and there you go. Works great as designed, at least in the 2 meter band, and other parameters you can look at as interested. So, okay. I know that was a really quick run through. Again, if you have more questions or want to get into this in more detail, feel free, to call us or bring us back for another session. And with that, I will pass it over to Mike, CDN. Take it away.
So thanks, Mike. That was good on the antenna. So I'm going to do just really, really fast, do some stuff you can do with radio circuit analysis and some component analysis, and look specifically at some filter, looking at how to measure some filters, and then also how to measure unknown capacitance and inductance values. Okay, so for measuring filters, and Dean covered a little bit, so I'm going to go really fast, but there are several measurements that we're interested in. The S21 is the primary one, and that measures the forward transmission characteristics of your filter. It'll show you basically your band pass, stop pass, where your signals will be attenuated, and your insertion losses. So that's primarily what you want to look at when we're doing filters with this little device. So for each one of these measurements, the S21 and the S11, and again, Dean covered some of this, there's various ways you can display it. And probably for filters, the most important one is the log magnitude. And that will show you the dB frequency response and insertion losses of your filters. Let's see. And Mike talked about the NanoVNASaver, the PC software you can run because the screen is quite small. I have the smaller unit. But what's nice about looking at it on the screen, if you're tuning a filter, if you have like variable capacitors or something, as you're tweaking the capacitors, you'll see it immediately responded on the little screen. Versus on the PC software, you got to keep hitting and do like another sweep and another sweep, so doesn't get that immediate feedback. So looking at it on the little screen is nice. Then once you get it where you want it, maybe hit it on the PC version of it, and then you can capture it. And again, this NanoVNA saver program is really, really good for that. Also, nobody mentioned that you can dump not only a screenshot for posterity's sake and keeping it for characteristics, but also as a touchtone files that it will dump out. And that's real handy if you want to do some like stub matching or something like that. You may want to pull it into another program, feed it into like EasyNet or SimSmith or something like that. So it's a really handy way to have the programs work into each other. And Dean mentioned this W2AEW, excellent, really good resource. Getting ready for this, the first thing I thought was when I bought this thing back in September, a couple of years ago, first thing I did was I built a little filter, and I forget what the heck I built, but I found it down there in my box. I'm thinking, okay, what is this thing I built? So I just hooked it up and just did a wide sweep on the Nano. So you can see here on channel 1, which Dean said is port 2, S2, is showing the S21 parameter as a log magnitude. So that is shown in blue. And I went since I didn't know where this thing was designed for, I went from 500 to 500 megahertz. And I can see over on the left-hand side of this, it looks like a low-pass filter. So I swept it again. Now this time I went from 500 to 50 megahertz, 500 kilohertz to 500 megahertz, 50 megahertz. And now it becomes a little more clear that yes, indeed, this looks like a low-pass filter. Then I ran it, once I knew that, then I ran it into the PC, the NanoVNASaver program. And as Mike said, there's analysis you can do. So here I did a sweep analysis of a low-pass filter, and it does indeed tell me this has a cutoff frequency of 27 megahertz, and it gives you the minus 6 and minus 60 dB points. So really, really handy. So from our makers group, this is the first shot at our low-pass filter. So the schematic, and this is breadboarding, just to get an idea how this thing was going to react. And then here it is. So I've got this just clipped on with alligator clips. I didn't show the VNA in there, but the NanoVNA, but it doesn't matter. It's symmetrical. So one side is the S11 or the S2 port, and the other side is the S2 port, S1 port, S2 port. And here's the sweep coming out of the thing. So again, it's a low pass filter. So I ran the sweep analysis, and it shows us we have a cutoff frequency of 8.2, and that's pretty much exactly where we wanted it. So that was a good test, and knew I was ready to build it for real. And this is my version of the bandpass filter that Dean showed a picture of his earlier. This one has variable capacitors. So as we're building this thing, we're trying to tweak it to get the bandpass right where we want it, and also to have nice attenuation. So again, the circuit, this is it in my radio, and here is the sweeps from the screenshots on the actual device itself. So the one on the picture on the left, I've got a really long sweep from, I think that's 1 megahertz to 30. And then the one on the right, I just narrowed it down and swept from 6 to 8. And you can see here, it's got, the classic shape of a bandpass filter. And then on the NanoSaver software, again, that gives you, nice plots. You can save it for posterity, and you can do the sweep analysis, and this time selected a bandpass filter. You put the red cursor in what you think is your filter's bandpass, and then you run this analysis, and it gives you all this nice data on it. So really, really handy. Okay, the next thing that you can do with this, moving from filters, if you wanted to find capacitance inductor values, if you don't have, a real nice inductor meter or a capacitor meter, you can use this little guy in a couple of different ways. You can either create a series tank circuit. So if you have an unknown inductor, for example, you can put it in series with a known capacitor, and then using the nano, you can see with the phase shift where it's resonant by looking at the phase shift, and then use a simple calculator, an online calculator, or if you're good at math, you can punch it out yourself, and it will let you know what your unknown is. If you have an unknown capacitor, you use a known inductor. And then the second method, which is much, much easier, is to sweep your device under test with a large enough range so that you get some 50 ohm impedance points, and then you can simply read off the value. So I've got a real quick demonstrations. And this demonstration, you can see at the top of the picture, I've got my wound inductor with a known capacitance value. And on the nano, you can see the phase shift, the blue line. So at that point where marker 2 is the phase shift frequency. So at 29 megahertz up in the right-hand corner, it says 29 megahertz. So now you can use that. You can plug it into an online calculator or run the math yourself, and it'll tell you what that inductor is for that tank circuit to resonate at that frequency. And I've got the reference here if you want to watch his YouTube video that explains how to do this. There's a link to the online calculator. Again, this was a inductor that we wound for our bandpass filter in our maker group. The target was 2.28, and using this method, I got 3.0 microhenries. Now, I did a calibrate, but my leads aren't real good, so there's definitely some errors in this, and I just threw this together this morning, so I didn't get a lot of time to refine the effort. And the second way is to plot it over a long enough sweep, as I said, to where you find a 50 ohm reactive point, which is the 90 degrees on the Smith chart. So here you're looking at the Smith chart. So this on this side is R open, right? 0. This is shorted, and so up here it'll be your 50 ohm point. So you just move your marker. Unfortunately, I can't see the marker. It's off the top here, but trust me, it's right at the very top. And you can see here 90 degrees. So that's the 50 ohm spot. And then right here, you can read off the frequency you're at. And then here's the reading, 2.0 microhenries or 2.06 microhenry. And again, the target was 2.8. So that was for an inductor. And here's again my inductor I was measuring. And then here I did the same thing, but now using a variable capacitor. So again, it's the exact same thing. You hook it up, your device under test. In this case, it's a variable capacitor. I swept it over a large range from 1 to 100 megahertz. Looked for the 90 degree. In this case, it's a capacitor, so it's minus 90 degrees, minus J50. And then from there, you can read it straight off again. So here it's, okay, here it's the top one, it's fully engaged, and I get 190 picofarad. And the bottom picture is fully open, and I get 43 picofarad. And on my capacitor meter, I read the range of this variable from 25 to 150. So not bad for a quick throw it together in a few minutes. So that was pretty neat. This is something I did back when I got the thing at the very, very beginning, back a couple years ago. I just built a little thing, and I was curious whether those snap-ons have any effect on my choking or not. So I just threw this on here and ran a couple plots. I did this again this morning. So no snap-on the left and with the snap-on the right. And you can see, using, again, the S21, the gain, which is the log mag, you can see with no snap-on, there's no attenuation at all. But with the snap-on, it drops off, fairly decent. So not great, but not bad for a snap-on off of Amazon. I don't know what the mix is or anything. Next thing in our makers group, we've been told that we need to put these ferrite beads on our power lines to keep the RF out of the power supply lines. So I thought this morning, well, are they any effective? Do they actually work? So just took my ferrite bead, ran a few turns to it, stuck it in my jig, and ran it. So here on the left is 3 turns through that ferrite, and on the right, I decided to put a couple extra on there just out of curiosity to see what it did. And it did make quite a bit of difference. So the sweep is low. So I'm at 1 hertz to 30 megahertz, right? It doesn't do DC. You can't put DC in this thing. So I went as low as I could. The plot goes from 50 kilohertz to 30. But you can see that it attenuates pretty good. So I got my red marker there at 7 megahertz. So with 3 turns, it's down at what? Minus 18 dB, and with 5 turns, it's down minus 26 dB. So it makes a big difference. A few extra turns might be worth it. And that's it for a quick run through.